Dear friends, today I am going to discuss with you the very important theorem related with the phase space, Liouville's theorem. Okay. This theorem states that the volume V enclosed by a closed surface in the phase space is always constant as when the surface moves through the phase space. Phase space is a space of a dynamic system. You know what is the phase space of a dynamic system? Dynamic means a system in which some particle is moving, some particles are moving. That's called the dynamic system. Phase space of a dynamic system is the set of all the possible states of the system. Mean all possible states. Those states describes the dynamic system at any time. Okay. Now you know in a phase space is a n-dimensional system in which there are n positions and n momentas or n velocity, you can see. So it's an n-dimensional system. Okay, phase space is a n-dimensional system. Now, in case of the two-dimensional system, to specify a particle with respect to its position and momenta, we need two position coordinates and two velocity coordinates. That means 4 coordinates are required for one particle completely. Now you know in case of only one-dimensional space, now let's consider one dimension. In one dimension, the particle is moving only along the one axis, one direction. Like if the particle is moving along x-axis, then at any time t, we need only one coordinates for position and one coordinates for the velocity or the momentum. Dimensional motion, then only one coordinates for position and one coordinate of the velocity. What is velocity? X dot. X dot means dx over dt. Okay. Now we are having a space. You know, the particle is one dimensional. Then we are having x-axis, mean position coordinate, and the velocity coordinate. X dot means velocity from the x-axis and having different velocities. Okay, so this is a phase space because phase space is a combination of velocity and position space, or you can say momenta and position space. Now at some another time, this phase space, it moves from this position to this position. Now what it means? It implies that there is no change because this space is going parallel and at here. So when it shifted from here to here, there is no change with respect to velocities, particle velocities. But position, there is a shifting in position. Position is shifted. So the particle now having it the different positions, but with the same velocities. Now going from here to here, so there is a change of the phase space with respect to the position and with respect to the velocity of the momentum. So this theorem states that, okay, no matter how the system evolve, the area contained within these points will always remain constant. Okay, this is the statement of the theorem, and we have to prove it now with the help of mathematics. Okay, now another property of the phase space is existence and uniqueness. Phase space is having a property of the uniqueness also. Like we are having a trajectory or a path of the phase space. So this is a phase space, and there is another phase space, and both are interacting at this point and this point. So this is not allowed because the phase space is having a property of uniqueness, because if they intersect, that means the particles having this at any time, at a particular time, particle occupying the same position, which is not possible. One space is occupied by one particle only. A particular space can be occupied by one particle, not many particles. So intersection of the phase spaces is not allowed. So this is a uniqueness. So important property of a system evolving, there's a phase space is evolving through, this is through, evolving through the phase space is uniqueness. That is, every orbit through the phase space is unique. So this is a property of the uniqueness of the phase space. So I already explained this is not allowed. Why not allowed? These lines, very important. Okay, now let us consider a simple harmonic oscillator, mx double dot. X double dot mean x dot mean velocity, and x double dot mean acceleration. This is mx double dot mean acceleration is equals to spring constant into the displacement. So let there is some mass with a spring. Okay, massless spring, and a mass is attached here. So if it is pulled along this side, so it will start oscillating like simple harmonic motion. Okay, so at any instant, it is at the this spring is oscillating. Okay, this is at the extreme position at any instant. When it is at the extreme position, just for a moment, it is at rest. It is at rest means it is not having velocity or the momentum. So momenta is along this side. So that means momenta is 0. Okay, that is we are on the x-axis, and from the mean position, the mass is at some distance. So that distance is from here to here. Okay. Now what happens at some other moment? At some other moment, this mass, it moves from this extreme position to this side. When it moves, what happens? The compression starts, compression. Okay, and when the spring is compressed, its position, this is a momentum axis, this is the position axis. Now its position, like it is going this side. So what happens? its distance is decreasing, but its velocity go on increasing, and hence the momentum. So this line moves like this. The point was here first of all, but when the mass moves this side, the trajectory becomes like this. What it implies? That you are moving along this side, mean x is decreasing, because when it reaches to the mean position, then x becomes 0 and the mass gains the velocity and hence the momentum. So x becomes 0 and momentum then becomes maximum. Momentum becomes maximum. So momentum becomes maximum. So now you are at here. This is the mean position. And mean position, the distance, the curve is moved like this trajectory. That means when you are at here, that means x is equals to 0. Mean at the mean position, no x. But momenta in magnitude is maximum, or the velocity is maximum. Now coming to the then mean to this extreme position, it is more compressed and mass goes to the other extreme position. Okay, now what happens to the trajectory? The trajectory, it moves like this. Now x is increasing and coming here. So here again, like the speed or the momentum is decreasing, but x is increasing in magnitude. So you are at here again from this was the mean position. In magnitude again, this distance is maximum, but the momentum goes to 0. So this is the position where the momentum is 0, but distance in magnitude is maximum. Okay, and when again, due to inertia and elasticity, the ball, moves this side. When it moves this side, okay, it approaches to the mean position. When approaches to the mean position, this x again go on decreasing and velocity go on increasing. So when you reach at here, when the ball reaches at here, again what happened? At the mean position, momentum becomes maximum from here to here, and the distance becomes 0. Again it moves to this extreme position, then it follows this path. So what it is, okay, this is the phase space, because this graph shows the variation of position and momentum or the velocity. So this is the trajectory of the phase space. The mass will go on oscillating, but the volume enclosed by the phase space remains constant. That is the theorem. So this is a circle, phase space is a circle. So area enclosed, Now there is an approximation here for this theorem, that natural referring to system for which Hamiltonian kinetic energy plus potential energy, whose Hamiltonians are not dependent on the time. So now we prove the theorem. Now consider first of all, this is the volume enclosed by the phase space at time t equals to 0. Now what happened to the other time, t plus delta t? Volume increases by a very small amount. This much volume increases by a very small amount. So I shown a element, I shown an element in the space where the volume is increased, volume of the phase space is increased, a small element, and I drawn this element at here. So this is the element. Because it's a volume, I'm talking about volume. Volume is area into distance. So this is having area. This is area dA, and the height. Height means this distance. This distance is v vector delta t, because velocity into time is the distance. Now the volume encloses by the element. How much? Now consider one thing in mind, because this area is dA, we have to take, vertical height is required for the volume. For vertical height, there's a dot product of the velocity with the normal vector. Mean this is the perpendicular component of the velocity, which is required for the calculation of the volume. Perpendicular component of the velocity multiplied by time becomes the distance, and this is area. Volume becomes volume of one element. This volume of one element. Now dt is taken to the left hand side. Dt is taken to the left hand side. So this is rate of change of volume of one element. Now consider a phase space having some points. Phase space, is characterized by position and momentus or velocity. Let this is a coordinate, this point is having coordinate x, y. Now along this side, this distance is how much? Delta x. And half distance is delta x by 2. Now I'm writing the coordinate for this point. So x plus delta x by 2 mean this distance, and y is the same. Now I'm interested for writing coordinate of this point. So x minus delta x by 2y. So now this is delta y. And coordinate of this point, here x is the same, but y, there is an increment from here to here. That is y plus delta y by 2. So coordinate of this point is y minus delta y by 2 and x. Now we have to find, now we are integrating. Why integrating? Because for finding the total, mean this volume, increased volume. So there's the integration. Now normal component of the velocity and area, how much it is? First of all, we are writing this normal component and this area into normal component. What is this area? Delta x. What is velocity at here, at this point? Because this is a vertical line, we'll write velocity Vy at this point. So it is Vy at that point x, y plus delta y by 2 into area delta x. Now we are writing this is the area and this is the vertical component. The vertical component means velocity at here. It is Vx and coordinates are like, okay, and multiplied by area. How much this area is from here to here? It is delta y. So into delta y. Plus is not plus, minus, sorry. Now what we're like, this area is taken. Okay, then velocity is along this side, mean along negative direction. So that's why negative sign here. The velocity at here into this area. Okay, and lastly this area, and again velocity along this side, which is again a negative. So minus again. So total, so this part is splitted into the 4 terms with respect to the phase space. Now combining the terms of delta x and combining the terms of delta y. Okay. Now delta x taken as common, delta y taken as common from here. So multiplied and divided by delta y here, and multiplied divided by delta x to the second term. Now we consider what it is. So if we are having a function, now here the value is x and total span is delta x. So this point and this point having coordinates like this. So there is some function, change in the function divided by delta x. This is called, curly f by curly x. So with that, what it is, what this vector is, very simple. This is, curly Vy by curly y into delta x delta y plus partial differential of Vx with respect to x delta x delta y. So it is common. Now what this factor is, so if I consider it in 3 dimension, similarly in 3 dimension, we will write it like divergence of V. When you open the divergence, you got the same in 3 dimensions. And then delta x, delta y, delta z in 3 dimension, this becomes actually volume dV. So we change the surface integral to, here it was the surface integration, okay, and converted into the volume integral. Now this is again now this is Q means position and momenta, phase space, and there is a point in a phase space Z. Z is characterized by Q and P, position and momenta. And what is the velocity of this point Z, which is in the phase space? Velocity is Z dot. Z dot means Q dot and P dot. And in terms of Hamiltonian, you know what is Q dot? Partial derivative of Hamiltonian with respect to P, and minus of this P dot is partial derivative of Hamiltonian with respect to Q. Okay. Now you know here the divergence of V. Okay. If you put the value of the del, and then you know here, because it's a dot product, so if V, you know, V is Z dot and it is equals to this, then del dot V will be equals to curly by curly Q dot plus curly by curly P dot, the properties of the divergence. So the property of the divergence, if V is equals to V implies to Q dot P dot, then del dot V will be written like this. Now substituting here Q dot and P dot from this relation. So writing here the value of Q dot and P dot. So it is equals to, you know, 0. That comes out equals to 0. And hence the theorem. Hence the theorem. It implies that the volume of a phase space remain constant. It cannot be changed, or it is not a variable with respect to time. Okay, V remain constant. That is the proof of the theorem. Okay, the phase space may move through the, you know, the phase space of a system may evolve, but its volume remain constant. Okay, it is not a function of time. This is the proof. Thank you. Dear friends,